Hello, Mr. Sorrentino here again, doing another one of my videos for Math 31. This one's going to be on section 6.4, matrix operations. We had learned about using matrices to solve systems of equations, um, and there are other methods we can use matrices to do that. However, they do involve us doing some operations, one of which in particular is multiplication of matrices in order to do that. So we want to learn something about how to perform various operations on matrices before we go much further with this. So the first example, you're given these matrices, and I'm going to do these mostly by example. You're given these matrices here, and you're asked to carry through some addition and subtraction and things that you see below. Now, these first ones involve addition, subtraction, and scalar multiplication. Scalar meaning that I'm multiplying a matrix by a number. More definitive, I'll say a constant. We're going to eventually learn how to multiply two matrices together too, because you can certainly do that. There really is no division of matrices. We do learn how to multiply by inverses, but that gets into the next that gets into a later chapter, so we'll get to there when we get there. So, as far as adding two matrices together, given two matrices that have this, they have to have the same dimensions. So that's what this is all saying here. All this mumbo jumbo here is saying that they have to have the same dimensions. Sometimes they call that the order of the matrices as well. But, they have to have the same number of row and number of columns. If they don't, you can't add them or subtract them. And all you would do is just add and subtract the corresponding parts. So, I'm going to take the number in row 1, column 1, and add it to the number in row 1, column 1 of the other matrix. Same thing as we go along. It's pretty straightforward. And the scalar product, if I multiply a matrix times a constant, then every single number in that matrix gets multiplied by that constant. It's not a row operation, it's multiplying by a constant. And they do show some properties over here which, some of them are just kind of go along with the properties you already know so much with them. Addition of matrices is commutative, associative, and things like that. There are matrices, that have identities and inverses. We'll talk about those as we move along the line. So if these are the matrices that we're given, and we zoom out a little bit here, you're asked to perform these operations down here. So the very first thing, A plus E, I'm just going to rewrite the matrices. So as you can see here, they are both 2 by 2 matrices. They have the exact same dimensions, so I can in fact add them. The result was also going to be a 2 by 2 matrix. And all I have to do is add the corresponding parts. So I'm going to add the 3 and the 2 and get 5. The negative 4 plus 1 is going to give me negative 3. The 2 and the 4 is going to give me a 6. And the 1 and the 9 is going to give me a 10. And I'm going to show you, we'll take that back, let's see. It's a negative 9. I know there was an issue with it. Negative 9, so that should be a negative 8. You can see a copying error can sometimes throw you off. Now you could do these on the calculator, and I will eventually show you how to do some work on the calculator momentarily, how to put matrices in and do various things. But you can certainly add the two matrices together as well, using very similar things than what you're about to do. But for addition and subtraction problems, I would say it's not really worth using the calculator for it because of the fact that if you're using you might find out it's going to take you longer to get it into your calculator and set up than it would be for you just to do the operation. Addition and subtraction should be something that isn't extremely difficult for most of you by now. And the numbers you're going to be dealing with in these matrices under most conditions are going to be relatively small numbers. I mean, they're not going to be like, billions and things like that. So, so you really don't have to worry too much about, you know, putting it into the calculator to check it. I mean, you could if you want to, but you're going to find out if you do, you're wasting more time getting it into the calculator than it would take you if you just wrote it out, decided if you needed to do it, and then done it. A minus B means I'd be taking the matrix 3, 2, negative 4, 1, and subtracting the matrix 3, 1, 4, negative 2, negative 2, negative 2. As you can see here, this is again, A is a 2 by 2 matrix. This one here is 3 by 2. 3 rows, 2 columns. 3 by 2. These are not the same dimension. Therefore, this is undefined. You can't do the subtraction. Negative 4 times f, or negative 4f. We might lose sight of those matrices up there, but you should have them on your sheet so you know what they are anyway. So that means I'm going to be doing negative 4 times the matrix 2, 0, 9, negative 1, 2, negative 4. Which means every one of those numbers in the matrix gets multiplied by negative 4. So this is negative 8, this is 0, negative 36, 4, negative 8, positive 16. 2c minus 3d. Well, as we just mentioned, in C here, 2 times C means I'm going to take matrix C and multiply all the numbers by 2. So I'm just going to do that as my first step. I'm going to write what 2c is. 2c is going to be 4, negative 2, 10 in the first row, negative 2, negative 6, and 20 in the second row. And I want to subtract 3D. So I'm going to go to matrix D and multiply all the numbers by 3. So I'm going to have 3, 3, and 12 in the first row. And I'm going to have 18, negative 18, and 21 in the second row. Now both of these matrices are 2 by 3. Therefore, I can definitely subtract them. I do have to be careful about how I subtract them though, because remember, I gotta be careful of signs and what all. So when I get an answer for this, 4 minus 3 is 1. Negative 2 minus 3 is going to be negative 5. 10 minus 12 is going to be a negative 2. Negative 2 minus 18 is negative 20. Negative 6 minus negative 18. Minus a negative is going to be plus. So negative 6 plus 18 is going to be 12. And 20 minus 21 is going to be a negative 1. And that would be the end of that one. For the last one, 2e plus 3f. Again, we know what e is. 2 times e means I'm just going to take all the numbers in e and multiply it by 2. So I'm just going to do that. Starting off, I'm going to have 4, 8, 2, and negative 18 plus 3 times f. I'm going to have 6, 0, 27, -3, 6, and -12. I went by columns that time. But as I look at these in more detail now, this is a 2 by 2 matrix. This is a 3 by 2 matrix. They don't have the same dimensions, so this would have no solution. And so those are the operations for addition, subtraction, and scalar multiplication. Now, when I have to multiply two matrices together, that becomes a different story and it becomes a little bit more involved. And I'm going to demonstrate it for you. They give you some verbal description of what it is. So if we look at what your textbook has for matrix multiplication, for an m by n matrix A and an n by p matrix B. So basically they're saying that the second dimension of the first matrix has to be the first dimension of the second matrix. We also sometimes call that inner dimensions. When we look at the two dimensions of the matrices written, left to right, the ones that are closest together in between are the inner dimensions. The outer dimensions would be the ones that are further on the outside. Basically, they're saying here that you would do A of I to 1 to B. It gets to be basically that you're going to be doing, you're going to be moving along the row of the first matrix and a column of the second matrix. And I'll show you what this looks like whenever we actually do the procedure. That's where some students have issues. It's a totally different procedure that they're used to doing for any other kind of multiplication. So I'm still using the same matrices that we had before. So I'm going to rewrite out the two matrices. So these are the two matrices, A times E. This is a 2 by 2 matrix. And this is a 2 by 2 matrix. Now they're the same dimensions, but it's not being the same dimensions that makes me able to multiply them. I can multiply them because when I have them written in that way, these inner dimensions are the same. So multiplication can be done because those are the same. The outer dimensions tell us what the final result's going to be. The final result is going to be another 2 by 2 matrix. Don't leave myself enough room here. I'm going to scooch this down a little bit. Again, if we lose sight of these matrices up here, not a big deal because you have them on the notes anyway. Here's how I perform the necessary steps. I'm going to move along this row and this column because this is row 1, column 2. Using the numbers from these is going to give me what goes in row 1, column 1, I should say. It's going to give me the number I should have in row 1, column 1. So what I'm going to have here is I'm going to have the 3 times 2 plus the -4 times the 4. And maybe I'm going to move this out a little bit if I can. For row 1, column 2, I'm now going to go down this column on the second one. So when I do my operations, I'm going to have 3 times 1 plus -4 times -9. Now I'm ready to do row 2, column 1. So I'm going to do row 2 with column 1. And so I'm going to have 2 times 2 So the first one in the row goes with the topmost in the column, and then you work your way right on the row and down on the column, plus 1 times 4. And then lastly, you're going to do row 2, column 2 to get what goes in row 2, column 2 in the final answer. And then I'm going to have 2 times 1 plus 1 times -9. So multiplication actually involves not only multiplying but also adding. And you're not just taking the numbers in their position. I'm not just doing 3 times 2 and getting 6 and saying that's what I'm doing here. That isn't how matrices work. It works that way for addition and subtraction. It does not work that way for multiplication. I have to basically a number that goes in for a certain row and column on the answer means that I've had to essentially carry through a set of operations between the row of the first matrix and the column of the second matrix to make it happen. So 3 times 2 is 6 plus a -16 is going to give me -10. 3 times 1 is 3 plus -4 times -9, which is 36. 3 plus 36 is 39. Two times 2 is 4 plus 1 times 4 is another 4. That's going to be 8. And 2 times 1 is 2 plus -9 is -7. So that's what A times E equals. Now when I look at E times A lot of students automatically assume, let's like numbers, that you can reverse the multiplication in a matrix. There are some matrices you can, but under most circumstances you're not going to be able to multiply. You're not going to find that matrices are commutative, and we'll demonstrate it here. Now again, they're both 2 by 2 matrices, so the inner dimensions match, which means we could do it. The outer dimensions tell us that the answer is going to be a 2 by 2 matrix. Make sure I have enough room. And so as I go through this, I'm going to do row 1, column 1 to get what goes in row 1, column 1. So I'm going to have 2 times 3 plus 1 times 2. Now I'm going to do row 1, column 2 to go what gets put there. And I'm going to have 2 times -4 plus 1 times 1. Now I'm going to do row 2 of this one and column 1 of this one, and I'm going to get 4 times 3, which would be multiplying these two, plus -9 times 2. And then lastly, I'll do that. I'm going to do row 2, column 2, and there I'm going to have 4. I don't want to do that there. We can use 4 times -4 plus -9 times 1. And so that's what I'd have to perform to make this happen, and that's going to equal, well, 2 times 3 is 6 plus 1 times 2 is 2, so 6 and 2 is 8. 2 times -4 is -8, plus 1 is going to give me a -7. 4 times 3 is 12, plus -9 times 2, which is going to give me a -18. So 12 plus -18 is going to give me a -6. And lastly, 4 times -4 is -16, plus a -9 is going to give me a -25. So notice that, these two are not equal. So under most circumstances, you're going to find that multiplication is not commutative. So be careful with that, and don't assume that it is. Don't assume if you calculate what A times E is, that you know what E times A is. Um, so, and this procedure works the same way when I have matrices that may have 3 rows or 3 columns or whatever the case may be. So let's try this one. Let me write out what B times C is. So there are those two matrices. Before I even bother to do any multiplication, even before you decide to put it on the calculator, it's probably best to do this. This is a 3 by 2 matrix. This is a 2 by 3 matrix. So the inner dimensions match. So multiplication can be done. And the final answer is going to be a 3 by 3 matrix. So I have to make sure I'm making room for a 3 by 3 matrix. So as I do this, and again, I'm going to go row, column, row, column. So I'm going to have this row and this column. So I'm going to have 3 times 2 plus negative 2 times negative 1. This row now with this column, I'm going to have 3 times negative 1 plus negative 2 times negative 3. Move this out a little bit. And then I'm going to do this row here now with this column. And it's going to give me 3 times 5 plus negative 2 times 10. That takes care of the first row on the first matrix. Now I'm going to do this row and this column. So I'm going to have 1 times 2 plus negative 2 times negative 1. Now I'm going to do this row and this column. So I'm going to have 1 times negative 1 plus negative 2 times negative 3. And then I'm going to have this row with this column where I do 4 times 5 plus negative 2 times 10. And now I move on to the last row. So this row and this column, I'm going to have 4 times 2 plus negative 2 times negative 1. This row and this column, I'm going to have 4 times negative 1 plus negative 2 times negative 3. You're seeing a lot of repeats on this because of the fact that I do have a column in the first matrix that's all the same values. That's not going to happen all the time, so keep that in mind. And of course, for negative this row and this column, I'm going to have 4 times 5 this should be a 1 times 5 up here. I was getting ahead of myself before. 4 times 5 plus negative 2 times 10. So when I work all of these out, I end up getting 8, 3, negative 5, 4, 5, negative 15, 10, 2, and 0. So that's B times C. Now what I would like you to do is use a similar process of setting it up, knowing if you can do it or not, and so forth, and now do part D. Okay, so really the only thing that's different with part D is I have the same two matrices but they're in a different order. Now, this is a 2 by 3 matrix. This is a 3 by 2. So the inner dimensions still do match. Cool. So I know I could do the multiplication. Now, though, I'm expecting a 2 by 2 matrix. So when I do this matrix here, I expect to have 2 rows and 2 columns, and that's it. And so when I go through and do this, I'm going to have this row with first this column. So I'm going to have 2 times 3 plus negative 1 times 1 plus 5 times 4. And then when I do this row with this column, I'm going to have 2 times negative 2 plus negative 1 times negative 2 plus 5 times negative 2. I'm now going to do this row with this column. So I'm going to have negative 1 times 3 plus negative 3 times 1 plus 10 times 4. And then when I do this row with this column, I'm going to do negative 1 times negative 2 plus negative 3 times negative 2 plus 10 times negative 2. And when I work all those out, following my order of operations and all, I end up getting that this is 25, negative 12, 34, negative 12. So as you can see, that not only are they not commutative, sometimes the results are matrices that are even different sizes. So if they're different sizes, there's no way they could possibly be equal to each other. So one more try. Try doing matrix E times matrix F and tell me what you get. Okay, so remember, you got to take it in the order that it's actually coming by. And so if I look at these two matrices and I rewrite them, now this is a 2 by 2 matrix. This is a 3 by 2 matrix. These inner dimensions do not match. So that means that this, in fact, has no solution. You cannot multiply those two together. If you had been asked to do F times E, where you had the 3 by 2 coming first and the 2 by 2 coming second, that would have worked because the inner dimensions would have matched. So this one you can't do. F times E you can do, which is another case, which is another indicator that there's no way that these matrix multiplications are commutative. And so that's how you do the matrix multiplication. Now, example 3, I'm going to show you how you can use your calculator to do some of these matrix operations. I'm going to focus on multiplication primarily, and how you can get your matrices set up on your calculator and perform the operations and so forth. So, so let's have a look at example 4, or example 3, I should say. Now here in example 3, this one's nice and tells you exactly what kind of matrices to set up and whatnot. Whereas some other problems you might be given along the way don't. And as I go through this, I'm going to explain like why what they're telling you to do is really the only way you could possibly do it. And relate it back to what we talked about with multiplication. Because when you use those rules for multiplication, knowing what you can and can't do, when multiplication can be done and when it can't be done, and even the process of how it is done will let you know whether or not you can actually do the multiplication, whether you set it up correctly, or even if you did both and you get an answer, does it mean anything? So you have this information here which tells you like you have 4 bakery items: white cake, bread, coffee cake, and sugar cookies, and the flour, milk, eggs, and butter needed to make each. So they want to see like this is what how much they use by weight for the various items. The unit cost for each ingredient is 15 cents for flour per whatever unit of measurement they're using for this, 28 cents for milk, 54 cents for eggs, and 83 cents for butter. So they're saying, okay, well, write this, what we have in this table is a 4x4 matrix that we're going to call M. That's pretty straightforward because, now one of the things I have to consider along the way is if I make M a certain way, it's going to usually affect how I'm going to make any other matrix that might have to be working with this. So M, now for the sake of our discussion, I'm going to also keep in mind what these various things represent. This is the white cake, this is the bread, this is the coffee cake, and this is the sugar cookies. And this was for flour, milk, eggs, and butter. They tell us how much it costs for each unit of this stuff, and they want you to make a cost matrix C, but they do tell you it's a row matrix, which means it's only one row. So C, based off of this, is going to be 0.1515, 0.28, 0.54, and 0.83. But again, I have to remember what these are. This is, how much it costs for flour, how much this costs for milk, how much this costs for the eggs, and this how much it costs for the butter. And of course, what I have here is dollar amounts. They tell you to find the product C times M. So they come out and tell you, they're saying that, and this is going to be what we call, D. They say for part D here, it should say part C. So the result matrix would be the result of that multiplication. Well, first of all, when I look at this, now the reason why they're saying to multiply by C times M, if I do C times M, now C is a 1x4 matrix, and this is a 4x4 matrix. So if I do a 1x4 and a 4x4, I could do that multiplication, and I would expect that D would be a 1x4 matrix. If I had chosen to represent this as a column matrix instead, so say I let C be a column matrix, they didn't give me any direction. There are a few problems where they don't really give you any direction. And this would be my F, M, E, and B. 0.15, 0.28, 0.54, 0.83. Now, first off, this being a 4x1 matrix, I couldn't do C times M. So C times M would be no solution. I'd have to do M times C. The problem is, like, what do I get out of each circumstance? One of the things that we mentioned before is, if I had M, I'm going to say M times C1, just to keep this straightforward. This being a 4x4 and this being a 4 by 1, I can multiply it in that order just fine. But I have to also think about what would be the result I would get as well, which is why sometimes I have to make the decision whether it's a row matrix or a column matrix. Here they told us they were nice about it. If I'm doing C times M, C being the row matrix, again, I know I'm going to get a 1 by 4 matrix. And I know that because I'm keeping basically the row heading of the first matrix C and the column headings of the second matrix M. Knowing this lets me answer the question right away of what it is that, for part D, what does the resulting matrix represent? Because what I have here is I have the bakery items, the white cake, the bread, the coffee cake, the sugar cookies, and I have the dollar amount. So basically it's going to be the cost of producing each item. I don't know what those amounts are yet, but that is what I'm going to get from this. If I had tried to do it the other way using a column matrix and did M times C1, again, I have a 4 by 4 matrix, a 4 by 1. The inner dimensions work so I could get an answer. My final answer would also be a 4 by 1 matrix. But what would I have? Again, I would have the row headings of the first matrix. I would have the F, M, E, and B. I'd have the column heading of the second matrix. This seems to say that, I'm going to have a cost for flour, a cost for the milk, the cost for the eggs, the cost for the butter. What this would basically tell me is, when I produce these items, how much money in total am I spending for each of these ingredients? It's not going to tell me how much I'm creating for each item. So as a result, what I get from each matrix could be a little bit different. And so for this, if I had chosen to do a column matrix, I wouldn't be able to figure how much it costs for each bakery item. I could tell you how much I spent in total for each ingredient. I could say I spent a total of X amount of dollars for flour, X amount of dollars for milk, so forth and so on. And so that's, one of the things you have to always be considerate about, like what you're looking for, because sometimes they'll tell you what you're looking for. Find a matrix that represents the cost of each item. We have to figure out, well, what kind of matrix do I need to set up that goes along with M, and when I multiply it to M, in what order, how am I going to get what I need there? So, that can be a little bit tricky if they don't give you some of the information. Typically, you're not going to be asked to set up a matrix from a table. You'll have a system of equations you have to set up, and then it's a little bit more straightforward about what you do. So don't be too concerned about, picking whether it should be a row matrix or a column matrix and so forth. That's a decision you usually don't have to make, and it's a decision you won't be tested on a whole lot. So I know the cost of producing each item. Now I need to go back and figure out what the product of C times M actually is. And so now it comes time to use the calculator for this, because it does help streamline things a bit. So let's pull out the calculator here. And let me quit out of this, clear this out. I want to be able to multiply two matrices. And I'm going to try to make sure I can see both of them as best as I can. Move that over here. I want to have a matrix M and I want to have a matrix C, and I want to do C times M. So I'm going to let A, because I could do matrix C, but this doesn't get, but if I come here to hit second in matrix, under names, these are all the names I could give my matrices. It only lets you go down to J. So you really only have 10 matrix names you could give it. Okay, so I can't find a letter M. So I'm going to let matrix M B matrix A. And so I'm going to say I want to come here and I want to edit this matrix. Matrix M is a 4 by 4 matrix. Not 44. 4 by 4. And all I have to do at this point is just type in the numbers that I have in there. So I'm just copying, I'm just typing all the numbers in, hitting enter each time, and it just moves along the matrix so I can fill it all in. So this is my matrix M, it's in under matrix A. If I come back to second in matrix again, I can see now I have a matrix that's 4 by 4 stored in A. I'm going to go to edit, and I'm going to go to matrix B. I'm going to let that be C. And C was a 1 by 4 matrix. So 0.15. Again, I'm just going to copy what I have there. So going through the menus and doing all this typing takes its time. So you can see why in instances of multiplication, it's best to use it because, it'll give me an answer right away and I don't have to go through the multiplication process. But for addition and subtraction, once you realize you can actually do it, just add the subsequent numbers together or subtract them. It makes it a lot easier. So now I'm back here. I want to do a calculation. I want to do C times M. Or in our case, it's going to be B times A. So now I'm going to come to matrix. I'm going to choose matrix B. So when I'm under names, it's just going to pull matrix B into my normal calculator menu times second matrix A. And I get my answer. So my answer, going to my answer for C times M now, I'm going to be able to put in what I have up here. That's going to be 0.97, 0.65, 0.8675, and 1.175. And again, recognizing the fact that, again, based up here, this is going to be my dollar amount. This is going to be the white cake, the bread, the coffee cake, and the sugar cookies. And so now I can provide a little bit more detail to part D. I know it's the cost of producing each item, and so that's going to be 97 cents for white cake, 65 cents for bread. 65 cents? I'll make sure, so double check the number. Yeah. Approximately, so I have to round a little bit on this one, 87 cents for the coffee cake. And about $1.18 approximately for the sugar cookies. And so that's what I get from this matrix. As I said, if I had made it a column matrix before and I had to do M times C, I would have gotten the total costs of each ingredient that I used for the items that I'm selling. It's not really meaningful because I really don't know how many I'm selling. It's like, the total cost for producing one of each item, which wouldn't be very practical. I mean, it doesn't really, help me differentiate. Whereas this, I know what the cost of each item is as far as that goes, so I know what I could charge for them. So, so if I had set up a column matrix for C instead, I would have gotten information that wouldn't be super useful. And sometimes you have to consider that whenever you're setting these problems up, if you're not given the information or given what kind of matrix is set up. So you're not going to be asked to do that a whole lot. There are some problems from the homework, though, that don't necessarily tell you what kind of matrix you need to use. So you do have to decide which one it is, or like what kind of matrix is set up to do it. So be mindful of that. And I'm talking about the homework problems that you're suggested out of the textbook. Pretty much the ones out of my math lab, they kind of say if you need to produce a matrix, they kind of have the matrix set up and they have all the blanks. And so you have to know what to put in there. But there are a few questions where you might be asked, and they show different dimensions. You have to pick the right dimension and put the right things in the right spot. So now the last thing that we're going to be asked to do here in example 4 is to be able to write a matrix equation that's equivalent to a system of equations. Now a matrix equation is not the same thing as using an augmented matrix. And we're going to show how to go through and do this in the next section. However, in this section, they do start the process off by having you be able to rewrite a system of equations as a matrix equation. So let's go to example 4 now. So basically in this section, they have a couple problems where they have you just write the equation out. Eventually, we're going to manipulate the equation to solve it. It's usually it's a quicker way once you've established something that you need to do to solve it, and we're going to talk about that when we get there. But basically, I want to be able to write this as basically the multiplication of two matrices equaling the right-hand side. I want to be able to write this as matrix A times a matrix we're going to call X equaling a matrix B. A represents the coefficient matrix. X represents the variable matrix. And B is the result matrix. I want to be able to write it into this format. It's not very difficult, mind you. It's very similar to some of the things we did when we were doing augmented matrices, except now we're writing the coefficient matrix as a separate matrix from the result matrix, whereas in having an augmented matrix, you kind of merge them together. And so basically, for this situation here, this would be my A, 3, 2, 4, 4, -5, -1, -2, 6, -4. I took all the coefficients that I had on the left-hand side times my variables. It's usually going to be a column matrix. And if we stop right there, as far as the left-hand side goes, if you would carry through matrix multiplication the way we would do them, I mean, so we would take this first row here and multiply by the column, that's 3 times x plus 4 times y minus 2 times z, which is what we had over the left-hand side in the very first equation. So, this is relying on you knowing your matrix multiplication, and it's going to equal, of course, 10, 15, and 9 on this side. So that's the answer for this. Now, what eventually we're going to be doing with this is we want to be able to turn this into an equation where we just have x equaling something, and that's going to tell us what the variables are. So it's going to mean if I have x equaling x, y, and z, and I have matrices with a matrix over here with numbers in there, that means that x has to be whatever this number is here. Y has to be whatever this number would be here. Z would have to be whatever this number is here. And if I was looking at this equation, say, well, that's pretty easy to solve for x. I could just say that, x equals b divided by a. There is no such thing as a matrix division. So that's out. And so we would have to say, okay, well, maybe doing the inverse of the matrix times b. Now, we haven't talked about inverses of matrices, but that's what we're going to be moving towards in the next lesson. So for the time being, though, that brings us to the end of this video. If you have any additional questions, please make sure to bring them up in class or come to my office hours. Until next time, or until you show up to one of those two places, I will see you around. Have a good day.